We are thrilled to welcome back Dr. Bob Smith, who has given many excellent talks to us here over the years. And I could go on for about an hour describing Bob's accomplishments and credentials, but I'm not going to do that. I'm just going to do a really quick summary, Bob. Bob is a distinguished professor of geology and geophysics at the University of Utah, where he has taught for 57 years. Bob got his BS and MS from Utah State and his PhD from the University of Utah. A few highlights from what is an absolutely amazing career. Bob has published over 225 papers in major scientific journals. He's been the major advisor of 70 graduate students, helping launch many distinguished careers. Bob has given thousands of abstracted presentations in national and international scientific and academic venues, and has been the recipient of numerous highly prestigious awards, including the United States Antarctic Medal, the United Kingdom Gold Medallion Award, that was also for work in Antarctica, the John Wesley Powell Award, which is the National Park Service's highest award, the George P. Woolard Award, which is the Geological Society of America's highest award, the U.S. Geological Survey Career Award for work in Yellowstone and the Tetons, and many, many more. Bob is also co-author of a terrific book titled Windows into the Earth, the Geologic Story of Yellowstone and Grand Teton National Parks, which was published in 2002 and is still a key reference for this whole area. I'm sure most of you probably own that book. And Bob has been studying and researching Yellowstone for 65 plus years and has actively helped us all understand this amazing place. He is truly the voice of Yellowstone geology. Please join me in welcoming Bob Smith.
No, it's working.
Okay.
Well, the topic, of course, is understanding Yellowstone's shaking and baking. Story that we've worked on for decades, and want to acknowledge my associate, James Farrow. He did his PhD with me, and he's now taking over some of my Yellowstone responsibilities. As I said, I've been working in Yellowstone actually 67 years. I started there out of high school, and I've been working there, and I established many of the networks, the research system, and I'm showing right here a picture of a high resolution GPS station. Let's see.
So Bob.
What? There we go. So this is a GPS receiver inside of that dome. And that's a stainless steel rod that buried a meter into bedrock. And we transmit the data over to the radio link, and the radio link is the antenna. This is the most remote place in Yellowstone, namely the Mirror Plateau. And the seismographs are right here. So I want to bring out the fact, I don't want you to know all these people, except for the fact we work with a lot of collaborators and associates, and with the Park Service, USGS, Berkeley, and et cetera. I do want to point out that I get funding from the Yellowstone Volcano Observatory, USGS, NSF, Park Service, and the Princeton Foundation. So we are highly indebted, and we appreciate their support. Now, I just want to show you this as if you haven't seen it. You've all seen it more than I have. Basically, Yellowstone is a shaking, baking geologic park. But it wasn't until the 50s and early 60s that the scientists put together enough information to recognize that it is, in fact, an active volcanic system. And here's a cross-section, of course, of the the falls of Yellowstone. This is a cross-section through one of these rhyolite flows that underlies the plateau of Yellowstone. I want to point out that I've used much of this information in this book right here, Windows into the Earth, and I have a copy here. And if you brought one, I'm glad to sign it. So that's now sold 35,000 copies. And the basic science, even though the book's older, the basic science remains the same. Now we have to think about Yellowstone. We're dealing with the last few seconds of geologic time. So if we take the beginning of the volcanism in Yellowstone as one day, and we go forward in my scroll into the Yellowstone volcanics, into the Yellowstone Quaternary system, 2 million years ago was the first caldera, 1.2 million, and then 600,000 over here. That's just the last 5 seconds of a day. So it's a very youthful and a very active system. And if you're out about in the country, of course, this is a map of Yellowstone. This is the outline of the caldera. Teton Range, 2.8, if you wish, billion. Yellowstone's about 2 million. And we're looking into the background of the Absarica Range, which can be as old as 4.9. And so we want to understand the interaction of this youthful volcanism upon this continent. Most hotspots occur in oceans. Yellowstone is the only major hotspot on a continent. And I'm going to go through and explain to you the fact that this is Yellowstone, and these are all the active processes that work at Yellowstone. Number one, there's a mantle plume at a depth of 2,700 kilometers, and it feeds fuel up, and that produces the heat flow and the magma. That in turn heats the surface, hydrothermal system. And on the right-hand side, the ground deformation tectonics drive the earthquakes, and the earthquakes are related directly to this system. So this is an active volcanic field. And so the mantle plume, I'm going to show you this in detail. This mantle, don't worry about the numbers right now. There's a deep mantle plume and a shallow crustal magma reservoir at a depth of 20 to about 6 kilometers. And we found by mapping the interferometric data, the radar returns, that this is a contour showing the fact that the whole caldera is going up, and these are, it's about 2.5 centimeters per year. So we want to see how this system works. Well, I want to make sure you understand what a magmatic system is. And here is an example of a test tube filled with resin, and we put it above a Bunsen burner. And of course, as it heats up, gases are exhaled from this fluid, and you can see the gases that are developing in this magma system, this analog. And finally, we're going to get enough, and it's going to blow its lid. Now, this is an analog of a meter or so, and we're going to talk about features that are, of course, tens of kilometers or hundreds of kilometers. So that's what we want to know about the correlation, or what about global distributions? This is a picture of basaltic flows in Hawaii. This figure didn't come out too good, but these are the chains of volcanic features along the mid-oceanic ridge, the East Pacific rise. And so these active volcanism, active volcanics, are the edges of active tectonic plates. And these kind of data were used to develop these models. Well, let me get to the point now. The first ash flows in the caldera were formed about 2 million years ago, and this is called the Huckleberry Ridge Tuff, named for the area of Huckleberry Mountain, just on the north side of Grand Teton Park. And this system, as you can see, exhaled a large area of rhyolites. And then second cycle, 1.3 million, we have superimposed the caldera and some lava flows in the Island Park area and in the Island Park caldera. And the third cycle produced the Lava Creek Tuff that we see today. That's in pink. And that Lava Creek Tuff is what you see when you drive into Yellowstone. It's a purple rhyolite, and it encompasses the whole Yellowstone Plateau. So 630,000 years ago. So this is a map showing the relatively young volcanic flows of Yellowstone superimposed on this caldera, the boundary I'm showing here in green. And the flows are oldest up to here, and they get progressively younger and younger till you get to the Pitchstone Plateau, which you drive through as you go into Yellowstone. And the Pitchstone Plateau and these other masses, the Madison Plateau, these are high-rimmed volcanic systems that really tell us much about the current volcanology. Now, as I said, most people think of hotspots out in oceans. Yellowstone is the interior of the North American plate. And this is an outline of the Western US showing the relative location of the hotspot. First of all, we have a San Andreas fault system over here. And I'm going to say, this Western US system has all the elements of plate tectonics. So there's the San Andreas Fault. Subduction is the Pacific Plateau Cascade subduction zone that drives the Juan de Fuca plate beneath the North American plate. And then there's lithospheric extension. That is from the edge of the basin range, all the way from the Wasatch Front over to the Sierra Nevada, has opened about 100 or 200 kilometers in its youthfulness. And of course, Yellowstone is here, but it's 1,500 kilometers from the ocean. So it's very unusual in that. On the other hand, it allows us to actively study it without having to rely upon an expensive ship like we do with Hawaii and other hotspots. Now, I'm going to show you this because this became very popular, and the National Geographic used our data to show there was a hot body beneath so here's an outline of Yellowstone. And beneath it, we mapped a body that starts near the core mantle boundary, 2,500 kilometers, and it rises up and it fuels some shallow magma reservoirs, and they in turn fuel the very shallow one of Yellowstone. I'm going to show you the detail. Now, what was interesting is that when we mapped it from the surface all the way down to the core mantle boundary, it wasn't a vertical volcanic plume. It's in fact tilted, and I'll show you why. But first, let me just say that Yellowstone, of course, is at the end of an active volcanic system, and this is my depiction of looking toward the Tetons from the north, and you're looking into a volcanic eruption that formed the caldera. So the edges of this active volcanic system are the caldera because the ground beneath this system collapsed, and it collapsed almost a kilometer. And we had active volcanism around the rim. We had high distribution of ash, clouds, and gases that could go as high as 80,000 feet. And so these system gets entrapped in the global atmospheric system. And so the effect of Yellowstone is much greater than just on the Yellowstone Plateau itself, because it gets entrained in the atmosphere and the stratosphere. It goes entirely around the Earth and gets deposited in different places. And some of the best deposits of Yellowstone or in the Gulf of Mexico. These are data retrieved from coring, as I said, in the Gulf of Mexico and the Western Atlantic. Well, Yellowstone earthquakes are shown here, and I named this belt of continuous seismicity, starting down around St. George, Utah, extending up along these north-south trends. And then when they get to Yellowstone, they circle around the Snake River Plain. And this system continues on all the way to the Canadian border. Well, this is the Intermountain Seismic Belt, and it wasn't recognized really. And I published a paper in the 60s outlining the use of these kinds of data, and that this belt was an active feature. And of course, it passes through Salt Lake City, among other places. So the question is, what are the effects comparable to the San Andreas Fault in California? Well, once you get into Yellowstone, these north-south trends of earthquakes come out of the Teton region up into the northern part of the caldera. Then we have this giant cloud of earthquakes that starts over here at Hebgen Lake, Montana, extends all the way over here to the Norris Geyser Basin. Well, I'm going to show you that these are actually related to the plate tectonic features. These down here are going to be related to active volcanic and hydrothermal features. Well, the track of the hotspot begins down here in the McDermott, Nevada volcanic field about 16 million years ago. And so I've just put in here the extent of centers of volcanism, not calderas. Each one of these could contain a dozen or more calderas, but these are center of volcanism, 16 million, 14, 12, 11, 10, and finally up to Yellowstone right here, as young as 600,000 years. And what wraps around like the bow wave in a ship? It's the bow wave of the North American plate that's moving, if you wish, the plate's moving at 2.5 centimeters per year across a fixed magma source in the Earth's mantle. It's the whole plate that's moving over this stationary source that gives rise to this track of volcanism. And notice that the seismicity is relatively low along the Snake River Plain compared to the surrounding, I call it the tectonic parabola. And it's because of the high heat flow and the lack of major stresses. Whereas over here, we get much larger stress release that gives rise to the active seismicity. So this is an active belt that I've put in here in the last 30, 40 years. And Yellowstone is right here. And this is a picture, of course, of the outline of the park. And this, well, it's not going to play. Well, you all know Yellowstone Park, of course, is right here. And of course, this high heat flux and the associated groundwater systems give rise to the Yellowstone hydrothermal features. And so the iconic Old Faithful is one that we all know about and people know about around the world. And this is a picture I took one late fall showing the extent of that active Old Faithful plume of hot water rising to about 120 feet. And then hot steam mists into the atmosphere. And these can be as high as 15,000 feet. That is the actual mist of the system. Here's an iconic picture, I say, of course, Yellowstone with the background. And this rim in the back where the trees are, that's the rhyolite flow. And of course, this is an active hydrothermal system. There's been billions of pictures taken of that. Here's some of the other important ones. This is Old Faithful in the winter. And if you've been to the Yellowstone Park in the winter and experienced Old Faithful eruption, because of the very cold temperatures, this whole system explodes up, up, up to heights, as I said, of thousands of feet above the actual system. And the hot water and steam spill over, as you can see right here. Guardian Geyser is a smaller system, but it's an example, again, of one of these hydrothermal features in the upper geyser basin. And then here's Beehive Geyser. And Beehive is in the middle geyser basin. And this geyser basically is a continuous erupting feature. Well, what's important here is that this is an aerial picture taken of Excelsior Hot Spring. Here's the Firehole River. You park your car and you walk up the trail. Park Service is well maintained. And then we come upon Grand Prismatic, one of the most colorful hydrothermal feature in the park. But also right here is the remnants of an explosion of Excelsior Geyser that erupted last in the 1800s, but it was witnessed by people who were in the park. And it broke out a hole in the ground that's about 100 meters wide. And this still gives off a lot of steam and hot water, but it doesn't erupt. Whereas, and neither does Grand Prismatic for that matter. So these are the iconic pictures of Yellowstone hydrothermal features. Now, I was flying in 1984 I was flying from Jackson to West Yellowstone, and I headed for the West Yellowstone Airport. And off to my right wing was this giant forest fire. It was an eruption of the biggest geyser in the world. It was an eruption of the system, North Geyser Basin. And you can see when this erupts, this feature can be up to 400 feet high, Steamboat Geyser. And it erupts, sometimes it's quiet for years, and then it will start and be active for a few years. And right now, last few years, it's been erupting several times a year. And I cannot say what it's going to do in the next few months, but it looks as though this thing is in a quiescent mode. But the point is that these hot springs, fumaroles, etc., they make up the idea that Yellowstone's a geologic park. It's not a visitor park, it's not an elk park. It's a geologic feature that's very active. Steamboat's the biggest or tallest geyser in the world. It can get up to 1,000 feet high, and it has excess temperatures at the fumarole of 300 degrees centigrade. So I said it erupts every 5 to 10 years for 20, 30 minutes. Erupted 7 times in the last few years. And I was flying. I'm a pilot, and I had a National Geographic photographer with me, and I said, "Whoa, there's this giant forest fire. Let's swing over there." I looked at my fuel gauge, and it was approaching like I better get to an airport and get some fuel. But I started taking pictures. I had 4 frames left in my 35 millimeter camera. And this is what we saw, the actual eruption of Steamboat Geyser. And then we turned and went West Yellowstone and refueled. But the point is, the chances of me taking that picture are 1 in 150 million. Now that's better than the lottery, is it? Or is it not? But the chances of this being taken, that's the only aerial picture known that I know of Steamboat Geyser. And, you come up here, you park come in the trails and you can walk right past Steamboat today. And it's a beautiful feature. It has been erupting, as I said, the last few times in the last year, 3 or 4 eruptions. Now, another thing that happens when you work in Yellowstone much of your life, 2009, I was at Biscuit Basin, which is the Upper Geyser Basin over on the west side. And I had been standing over here leading a little field trip. This thing went off right behind my back. I mean, literally 20 feet. And everybody had their cameras out. And I said, what's going on? I looked around and there was a hydrothermal eruption in the Biscuit Basin. And you can see it's throwing pieces of rock that are the size of 6 to 8 inches. Then they rise up to 50 feet. And then the hot water is erupted and it forms an apron of fluids that come out, they flow out, and they collect in that pool. So I heard this roar, and I said to myself, there can't be a truck behind me. And all these people were taking their cameras out. Well, it, of course, was an eruption. And this system, as I said, it was very close to us. If we'd been any closer, we would have had some dramatic effects on us. Here it is as it's cooling down. You can see this feature now is filling up from the exhumed water. You can see the water phase whopping down into that system itself. Now, this process only takes 30 seconds, so you have to be quick. But it's a very impressive thing to see and experience that. So there it is, the eruption, water coming out into the surrounding pool. Well, Yellowstone's an interesting place, and everyone says it has all the earthquakes that I'll talk more about, but this is a map showing the seismicity, that is the earthquake distribution, and their north-south features here, which are actually on volcanic vents that are buried only a few kilometers. But there's this big zone of seismicity that runs from West Yellowstone all the way to Norris. And everybody said, oh, that's a Yellowstone volcanic feature. And I said, now, wait a minute. So I actually modeled. Remember, in 1959, we had a magnitude 7.3 here at Hebgen Lake, produced a 22-foot high fault scarp, and it resulted in deaths of people in the region. And I modeled it as these are slices into the earth. They're slices of faults that go down into the top of the crust. And I modeled it to show what we call excess stress. So where it's purple, that feature has reduced the pressure on the ends. It's picked it up and it looks like a dog bone. We call it a dog bone stress field. And it's because in the case of Yellowstone, and then here are all out of the aftershocks in the 70s and 80s and 90s, and they occur in these lobes of high stress shown in red, and there's this deficit shown here. So this feature is very important. The point being, the earthquakes that are generated across Yellowstone are not from a volcanic feature. They're aftershocks of the 1959 Hebgen Lake earthquake. You know, a lot of people don't want to understand that till we do the math and the physics, and we can show clearly from the seismicity this pattern. And the earthquake rupture is, of course, related to tectonic. The plate is stretching. That's what is being shown here. But seismicity or Hebgen Lake aftershocks, and they can go on for tens to hundreds of years. So the effects of the Hebgen Lake earthquake in 1959 could well be going on for another 100, 200 or more years. And as they occur, they also stress the volcanic feature. So there is just a picture of it in more detail. That's the two falls, Hebgen Lake Fault, Red Canyon Fault, that are dipping to the south. And they come to the surface, they're shallowest up dip, and they get down to depths about 15 kilometers. Madison Plateau Swarm was very active and remains active in 2010 and 2014. Well, I want to show you how we do our science. And this is a picture of these are new seismographs that were just developed in the last 10 years. And they're called nodal, N-O-D-A-L instruments. And they are completely autonomous. They sit in the ground. There's a spike on the end you shove in the ground. They have a seismometer inside that measures the ground shaking at the top. There's a memory bank. These can run for 2 to 3 months unattended. So they're autonomous. And so we started working with these systems, and we used one summer up to 600. Now, if you've seen 600 of these things around Yellowstone, you probably haven't, because we don't put them in until the day after the park closes on December 6th. And the next day, the University of Utah is there with all kinds of seismographs, other equipment. And we've used these for some of these detail models. First of all, this is a map of the earthquake stations. And you can see that we concentrated on this zone of earthquakes coming across in the Hebgen Lake area. That's the Hebgen Lake Fault right there. Because we wanted to really see how these earthquakes could be monitored. And so we put in seismographs that are vertical component, 3 component, and then we put in what's called broadband. Broadband means they're very sensitive to longer period ground motions. Most seismographs are sensitive to ground motions of 10 or 15 cycles per second. But these broadbands can measure ground motion out to minutes. So on the other hand, they're not cheap, but we put this system in over the years. These are all the permanent stations that run today. And you can access all of these data at this website, quake.utah.edu. And we've set it up so that as soon as an earthquake occurs, it's posted. So you as a user, if you log into our website, can see the earthquakes the same time I do. Because we want the data out so people can see the time sequence of earthquake swarms, et cetera. So that's where you go, quake.utah.edu. And we get 5,000, sometimes 10,000 hits a day on our website. Where are they coming from? Primarily from China, the Middle East, Europe, Eastern Europe. People come from all over the world to our website because there's a group of people who are following Yellowstone all over. These are small groups. And boy, they keep on top of this stuff. And an earthquake occurs, suddenly my website is full of people's questions. And then somebody put my telephone number out, and I start getting phone calls from Eastern Europe, from Japan, et cetera. I've changed the number. Now, how do we get the data? This is a map showing all the stations, and these lines show the radial links that come in from seismic stations to Mount Washburn. You all know where Mount Washburn is? On top, there's a big tower, 3 stories high. There's a fire guard on top. And at the bottom, we have our systems that record this, and we have antennas that record data all around Mount Washburn. Plus, we send data to Sawtell Peak. You all know where Sawtell Peak is, Island Park. So when you're driving between West Yellowstone and Island Park, you look up to the west and you'll see this. This is the peak that has the big radome the FAA operates. So we're all interconnected, and we work very closely with the agencies, Park Service, FAA, et cetera, to allow this. Now, I'm not going to show you the details. This is a figure showing all the kinds of stations we have. Don't get into it. Look at the bottom. We record data from 47 stations and 160 channels at 1,000 samples a second per station. Now that takes a lot of computing and reliable computing. So we actually have two computer systems running side by side. So one goes down, the other one is there. And these data are immense in terms of numbers. Now, people here might have, in the oil industry, I've seen what's called a vibro-size. That's a truck that bounces up and down, and it's used in seismic exploration. And this is a vibro-size that we rented, and we brought it to Yellowstone. And what we wanted to do was to see if we could get signals from a system like this. I'm sorry you can't hear this, but the ground is shaking up and down at about 20 cycles per second. That's a pad that sits on the ground and has a piston that leaves the whole mass of the truck in the air. So the whole mass of the truck is pushing down on this 1 meter square pad. And this system vibrates, and we record, we have a seismic station inside of it, and we record this, and I'll show you the results of what we see around. It was 2020 we did this, and we put out 600 seismographs. Now, if you don't think that isn't a chore, we use those nodal instruments starting down at the north end of Teton up to West Thumb or Round Lake, but we concentrated on lines that crossed northwest, southeast across the caldera, because we knew there was something going on down here. And we ran this system for about a month. Oops. So there it is, the vibro-size, and we ran it only at night. Park Service would not allow us to run it before 10 p.m. and we had to stop by 6 a.m. Of course, the reason is there's people traveling all around, but at night, the visitor traffic is very low. So they allowed us to actually do this experiment. And this, while we were doing this, was amazing. We were out doing these vibro-size experiments, and an earthquake came right along. So we recorded an earthquake into these 600 seismometers. You want to talk about a lot of data. Man, it gave us data. And these are the seismic waves as a function of time for all these stations. So the closest station had the earliest arrival time. You get further away, later and later and later. Now, what we do is we measure these phases that are coherent, and we use those to do tomography, just like you do when you do radiology. And I won't get into the details of this. We also sit out there, all these stations, and we just listen to the ground vibrate. You know, the earth shakes all the time, everywhere. It's ambient noise. And its signals are produced by wind, by humans, of course. And we call it ambient noise tomography, we use these data, we collect them for months. Well, and then we put them together and we actually can create a radiogram just like you do when you go to a doctor. And here's what we discovered. We discovered, and these are the colors here. Blue is cold, internal is warm, lukewarm to hot to magma. And there, of course, these different depths, 3 kilometers, 4 kilometers, and top is 6 kilometers. So across the caldera, you can actually see this body. And this body was well mapped using these data. And I won't get into the details of the tomographic image, but we have a body that starts at about 6 kilometers or 4 or 5, goes down to about 20 or 15 kilometers. That's hot. And it's seismically low velocity. So when rocks get hot, the waves slow down, just like you and I talking. In the summer, the acoustic waves are slower than they are in the winter. These are acoustic waves. And this is acoustic tomography. And I published one of the very first publications on this methodology. And here's what we discovered. These are maps showing the velocity of the rocks. And this is using different kinds of data, but there's the one that really shows the extent of the low velocity body right beneath the caldera. Well, I've shown you the seismicity, and we're going to look at some of the features of the earthquake data. Again, these are zones of seismicity coming up from the Teton region, and this is that east-west cloud of earthquakes that are produced by aftershocks of the Hebron Lake earthquake, and these are volcanic related earthquakes. Now, what we found is Yellowstone earthquakes occur in very tight clusters in time and space. We call them swarms. And it's a very common feature in volcanic region. It is not very common in just cool tectonic regions, like the Teton Fault, for example, which you look at these swarms. And this is a map showing in blue the actual swarms that we computed from these data. And you can see in this period of time, we're getting 600 swarms. We were getting 3 and 4 big swarms a year. It's a lot of earthquake data. Seismicity through 23, pretty quiet. Again, there's this east-west swarm or trend with these swarms of earthquakes. Down to the caldera, the seismicity is relatively low for this period of time. Now, this period of time, the biggest earthquakes were magnitude 3. Now, magnitude 3, people feel them. So they report them on the felt page of the USGS or to us. 2024, Yellowstone's deadly quiet right now. Don't quote me. Here's our brand new systems. Again, I showed you pictures of that before. That's a GPS antenna, and there's a transmission system. And now we actually put out long tubes, and we record the ground shaking like in a hose. So these, in fact, we actually used hose. These are metal, but we've used hoses filled with a fluid. We just lay them out on the ground and put a sensor on the end, and they feel the ground shaking. This is an experiment around Norris Geyser Basin. Here's the Norris area. And we put these stations out, and you don't need to know where the details are. But this is an experiment because we knew Norris has a very active system. Guess what we found? We found these swarms of earthquakes. They go on and on and on. And this is an example. We get literally thousands of them. And these are mapped as harmonic tremor of the ground from a hydrothermal reservoir. Oh, here's one that's interesting. Everybody said, gosh, we're going to go to Old Faithful and find out what it's doing. You know what it's doing? Nothing. We can't even record an Old Faithful eruption, but we record these harmonic tremors that precede eruptions. So what we're doing, these are tremors of fluids coming into a reservoir, and then the eruption of the geyser just releases the energy, but it doesn't really cause much shaking on the ground. Now, when you walk around and you feel Old Faithful, you say, my gosh, that's what we actually record. Now, I'm going to show you some data on the northwest side of Yellowstone. This is West Yellowstone's right over here. We had a big swarm of earthquakes. You can see by depth, they started at about 2 kilometers and they go down and you can see maybe 4 or 5. And we can see this plain of earthquakes. This is a zone of earthquakes that comes out starting east of West Yellowstone and extends up into the backcountry of, well, West Yellowstone area. Now, we had a big earthquake swarm right here called the Maple Creek swarm. And this is a map just showing you, here's the Hebgen Lake earthquake. We wanted to understand, we had an earthquake sequence that started, this is Maple Creek, Yellowstone. I know you can't see the creek, but it's there. And here's what we actually mapped. These are earthquake cross sections in 3 dimensions. Well, that's 2017, 2018. So we can map out these plains in time, and we can map out the fractures which they occur. And we can actually do time-dependent sequences of these. I'm not going to get into the detail. This is a lot of new material. Well, the Librasize project, as I said, we put out seismic stations all over, and this is what we recorded. We recorded these are low velocity bodies. It's hot rock, very hot, down to a depth, as you can see, of about 10 to 15 kilometers. That's the Yellowstone volcanic system. And these are just some of the cross sections to give you an idea. We published that paper not long after we got these data. And that's what the low velocities are telling us. Again, the caldera at shallow depths is relatively, I don't say it's lukewarm, it's about 1,000 degrees centigrade. But once you get down into the magma, then we can get temperatures excess of 1,500 degrees. Well, what we wanted to do is map how fluids come into a geyser. So this is a cross section of a geyser called Old Faithful. So down at a depth of only 23 meters, there's a reservoir of hot water. These are heated by the magmatic system, which is much deeper. And so fluids rise in this system up through a fracture zone, then burp. We get a geyser. Well, we started looking at at this interval, if you wish, of time before an eruption at Old Faithful, and we could track this, then boom, and we would actually see then the post-eruption earthquakes. So we were actually able to use this. And here's the the hydrothermal system. It's going to start down at depth. It's going to rise up through a few hundred meters. When it gets to the surface, bang, we have a hydrothermal event. Well, we take these instruments. This happens to be a deployment at Old Faithful. It was 40 degrees below zero that day. This was like middle of December. And we recorded this Old Faithful eruption, which didn't really have a good signal. So we were surprised it has this precursor. And we can map the precursor and we can tell the time when these are the eruptions. And we can actually predict the time of the Old Faithful eruption by mapping these harmonic tremors. So we took this to the Park Service and said, look, you can go out there and predict within about 20 seconds of the next eruption. They didn't believe us until we showed the data. They believe us now. If you get around Old Faithful, you get things like this, tremors of the ground. These are different stations up around Geyser Hill. You've hiked to Geyser Hill, haven't you? Well, this is a system we put in detail, and we see these volcanic tremors and these bursts of energy. And they're related to, again, a hydrothermal reservoir. Now, when we actually map this thing, we know that this is the actual volcanic system. Fluids come up from there. It's made of crystals, exalt volatiles, and silica melt. That's what makes rhyolite. And so we want to map these things. Well, I said one time, where does Yellowstone start? Is it a shallow plume, like a plum, or does it go clear down to the Earth's mantle? And no one could answer that. So we put out instruments. We wanted to actually measure how these things would develop. And we did actual numerical models, put wax in a jar, heat it up, and the fluid rises to the surface. You've probably seen that in your high school days. Now, what happens, this is a model. I took a bottle of honey and I poured it onto a table, then I pulled the table away. So it comes down here and then it spreads out. So what you do is you invert that. And this magma model would be deep in the earth, and this magma comes up and it underlies the North American plate. And it goes all the way back in our models, 1,500 kilometers, about 10 inches. Well, this is this tomography. You know who this guy is. Oops. We use earthquake data and we actually calculate 4D data. So what we're trying to do is model, and here's a cross section. So there's a low velocity body in here, and then we record enough earthquakes. The waves come through this body, they're retarded because it's hot. So if you record thousands of these earthquakes, you can start resolving the actual magma itself. There it is. And that's what we did for Yellowstone. We used earthquake waves, recorded seismograph stations across the surface. We wanted to map the low velocity body, and we had earthquakes on the edges of the caldera, a lot of earthquakes, a lot of data. This is what we found. This is a low velocity body. It starts at about 1,000 kilometers and it rises up. So this is an isosurface of low or hot rock. So you can think of it as a candle. And it rises up to the surface and then it dives back down and cools off and it forms the Absarica Mountains. Their root is right beneath this system. So the Absaricas are closely related to Yellowstone, more than most people would understand. Well, that's what that feature looks like. It's the Yellowstone plume, if you wish. And our latest data show that this goes down at least 1,000 kilometers, and some new data suggests it goes 2,700 kilometers. It doesn't rise vertically like everybody puts in their cartoons. It goes to the northeast, southwest, northeast, finally Yellowstone. It's this wiggly thing of material going through the cold earth lithosphere and the surrounding mantle and crust slow the retardation of this system. The plate is moving from right to left in this model. Now here's Old Faithful. We wanted to map Old Faithful using the same methods. So here's Old Faithful, and we wanted to see this kind of a model would apply to Old Faithful. And there's where we found their hydrothermal reservoir. Old Faithful's just on the edge. Look at all the infrastructure over here that underlies the Old Faithful Inn and other features. So we've actually shown that the Park Service gets excited about this. And by the way, in the winter, there's no snow anywhere around here because of the high heat flow. And we did some modeling of the actual ground motions that come out of earthquakes. And we saw this big zone of earthquakes from the Teton Fault and the Hebgen Fault, but Yellowstone caldera is relatively weak. Now magma comes up and outwards, and as it comes up, it triggers little earthquakes all around the edge because it's cool. And these are the earthquakes that we actually record, and we can then deduce the structure of this body. Well, here's what we found, if you wish. We found a body, this is a steamboat geyser. We found a body depth of only about 100 meters, and one little zone comes up, that's Steamboat Geyser, and another one to the southwest. And this is just a rotation of that view. These are the hydrothermal bodies that feed, if you wish, Steamboat Geyser. Biggest geyser in the world. Here's the roots of them. Now, one of the things we discovered is that here's the Yellowstone caldera, but we found the low velocity body of Yellowstone goes clear up to the Lamar Valley. Those Yellowstone hydrothermal features are at depth beneath the Lamar Valley. And it's because the plate's moving across. Here's the hydrothermal feature in magma. It's burning. You move your hand across, and right in front of this system to the northeast is, if you wish, where the actual body is. Well, to the northeast. Well, I'm not going to get into this. I just want to finish off here and say, what are the hazards and risk? And I plotted caldera eruptions. They occur 0.001% per year. You know, once every 650,000 years. And then I plotted post-caldera flows, and I did the probability numerically, and then I did the risk. The risk is related to where this feature is with respect to human events. Well, the annual probability says Yellowstone is dominated by hydrothermal systems, and numerically it certainly is. But when you include the earthquakes are the biggest risk in Yellowstone. It's not the volcanism, not the hydrothermal features, it's the seismicity. And basically, we've shown, there's the caldera, we've shown the velocities in red are the low velocity bodies, 5 kilometers, 8 kilometers, 14. And this is a cross section from the Lamar Valley to the southwest across the Mallard Lake Dome at Old Faithful. And this is the body, and it's in percent change in velocity. This body to the northeast, the Sour Creek Dome, which is just north of Fishing Bridge. That's the hottest body, but that feature will clear up near the surface in Lamar Valley. Now, it's not right at the surface, but it's getting very close. Now, what do these big eruptions mean? I put this slide in to remind you, these are big volcanic eruptions that have occurred. And here's what these are maps of ash flow and eruptions in the Pacific Rim. they can have plumes of material that rise up to 20 to 30,000 feet. And the ash moves out, pyroclastic flows. That's what causes the damage, just not the volcanism. It's these flows of hot gases, steam, and water. So I go back to Yellowstone. It's truly a volcanic feature, a volcanic park, if you wish. And I've already told you it erupts, well, probabilities for me taking that picture was 1 in 150 million. How good is that? Now, as I finish off here, we plotted here the number of earthquakes in these red columns. And we plotted the Yellowstone swarms in blue. The biggest swarm was in 1984 and 85 on the northwest side of the caldera. Then I plotted also the ground motion, measured from GPS and leveling. You can see the ground is moving up, then there's a big swarm, and then the ground goes down. Then it builds up, goes down, builds up, goes down. That's inside of the caldera. If you're outside of the caldera, it's directly opposite. So when the caldera is going down, the area around Norris and West Yellowstone is going up. So they anti-correlate because you're taking fluids out of the shallow crust on the west side of Yellowstone, and you're putting them into these shallow magma systems. Now I had to show you this. We were in, this is the backcountry of Yellowstone, and we were in a very acidic system. And one of my students, and I said, don't sit down. I know you're tired, but go find a log, but don't sit down in the grass next to the stream. Because when you do that, the acid, of course, puts holes in your pants. So importantly, in Yellowstone, listen to your advisor. Oh, I'm going to finish off to say, I've worked all over the world, but I was the exchange scientist with the British Antarctic Survey in 1962 and 63. And I went to Antarctica and the South Pole. And just to prove it, here's a picture of me driving a dog team. See, I've worked around the world from the South Pole to the North Pole. And you know what the best place is? Yellowstone Teton. So thank you very much. And I'll answer any questions, I hope. What? Say again?
I have two questions. One is, you said you were going to talk about the risk, the possible risk to Salt Lake City.
Yeah.
And then also the plumes.
Right, that's the inter-mountain seismic belt.
The plume that comes down from, is that the way that all?
Okay, the North American plate stretches from the Wasatch Front, the Teton Front, all the way east to the Atlantic Ocean and the Mid-Oceanic Ridge. So the plate is breaking apart, not only on the San Andreas, it's breaking apart in intraplate mode that's outlined as the intermountain seismic belt. So if you go to the Teton Falls or the Wasatch, you stand on the east side of the valley, things are quiet, but they're stretching. So if you stretch this brittle across, it wants to break. And it breaks in earthquakes, because it's brittle. And that's what the intermountain seismic belt is. It's the zone of intraplate extension to the west.
And are all the plumes curvy like that?
Well, in the what? In the plume?
Right, like in
I
Hawaii, the Hawaiian.
have a whole talk on that. That's because magma, so the internal part of the Earth's crust and mantle flow. They flow 3 to 4 centimeters per year. And so it's like a pot of boiling water or boiling coffee. The material boils, but in the case of the Earth, it boils at 3 different levels of the mantle. And those boiling, there are 3 different zones. One goes like this, one goes like this, and one goes like that. And that's from the seismic tomography that we've done. But I modeled this and published papers on it. It's it's very fascinating. This Yellowstone is not simple. It's a very complex system. And the heat we see is simply the remnants of the active volcanism that's going on today. Right below your feet. Go to Old Faithful and you can stand there and say, oh, I know there's a hydrothermal body at a depth of about 1 or 2 kilometers right beneath my feet. I'll tell that to the visitor in March, or if they don't believe you. Just right.
Yeah, it's over the course of your 65 years in Yellowstone. Have you noticed, any trends where the geysers are getting more active?
Yeah, I mean, this is true. I started in Yellowstone out of high school. And I've worked there since 1956. And I've worked there ever since, except for time in the military. And the trends, the annual trends we see today are much the same we've seen in the last 100 years if we look at the data. There's nothing really unusual, except that the the caldera right now is deadly quiet, seismically, but these earthquakes repeat. Magnitude 7s repeat in the Teton Fault, the Hedgeland Fault, every 850 years. Now, the last one on the Teton Fault was 2,500 years ago. We're way behind. So we're charging the Teton Fault. That's why it's so ancient. So if I ask the question, do you have earthquake insurance? Yes, flood insurance and volcano insurance. You can buy, it's called natural hazard insurance, and you talk to an insurance company. And I have it for my home in Jackson and my home in Salt Lake, just so I don't get embarrassed.
I'm interested in what you're saying about aftershocks.
Mhm.
And I assume an aftershock is a ripple effect, right?
Well, yeah, when you,
And I want to know what's rippling, what's shaking.
oh, it's not rippling, it's solid earth, but if you take a rock and you break it, it stresses the sides of the fault. So it just increases the pressure. And the increase in pressure caused by the rupture is creating these aftershocks.
In what? The
Oh,
crust?
it's brittle rock, depths of only,
In the rock?
yeah, it's in brittle rock. It's nothing to do with the volcanism. I have a paper on that if you want to read it. I've written 230 papers on Yellowstone in my life. Oh, my book is right here. So
Bob,
where's my book?
Yeah.
Yeah, okay, if you brought one, I'll sign it.
Bob, we do have a question from Zoom, which I will read. Would the Snake River Plain be a good area to develop geothermal energy?
Well, that's an important question, and that's
Do you
been
wanna
looked at by companies, by the USGS, by universities. And the Snake River Plain is relatively warm compared to the side rims. And so that's why there has been developed proposals in Island Park. Because Island Park is very shallow northeast end of the Snake River Plain. And there's been drill holes put down at the Idaho National Lab to 10,000 feet, and they've mapped the whole heat flux out of these features. The answer is it's lukewarm compared to an active magmatic, compared to Yellowstone. But there's been a lot of proposals to drill and make geothermal steam systems of the Snake River Plain Island Park. And there was a proposal to do one at Island Park about 10 years ago, but they ran out of money. Putting a well, it's one thing to put a well in Texas into Cold Rock. You come up here and talk to the engineers and you say, I want to put a well down to where the temperatures are 1,000 degrees. These engineers just shake their heads and say, you can't be serious. Well, because a steel rod into the earth at these temperatures becomes relatively viscous. It can just move back and forth because it's not cold enough to remain brittle. Becomes viscoelastic. Did you raise your hand? Okay. Well,
Any other questions? So I have a question, Bob. Let me just get over here so I can talk to Zoom as well. Do you consider the Teton Fault part of the basin and range? It wasn't shown as part of the basin and range on one of the maps you showed.
it's really it's the Teton Fault. If I showed you I mean, we have a paper on all this. There's active faults from the Tetons all the way to Oregon to the plate boundary. So these basin and range faults are every 25 kilometers across Nevada. Each one of them has a fault, and then most of them dip to the west. But the Teton Fault, when it ruptured, it dips to the east, so it's an anomalous body. And so when the Earth, the lithosphere is pushing the whole western US plate, it's pushing against the Teton Fault and it locks it. That's why there's no earthquakes from Moose North, because it's a locked fault. And, but when you build up enough stresses, it's going to go. I said every 800 to 1,000 years, the Teton Fault ruptures in magnitude sevens. And we haven't had one for 2,600 years. I mapped them by dating from trenching of the actual quaternary history. Thanks, guys.